Hello, so this is section 5.5, video 1. This section is going to be quite complex. I just want to start off with this example where we're going to find the eigenvalues of this seemingly innocent 2x2 matrix. Something fun, my computer ran out of ink, and so I am recording this section's videos using my tablet, which is very old. As you can see, there is a headphone jack right there. But it works. So technology sort of came to the rescue, that I can get the notes pulled up on this. So let's start by finding some eigenvalues. So at least at the start, this problem is going to be fairly straightforward, right? We subtract lambda off the diagonal entries and calculate the determinant. And surely, at this point, if we're starting off with an example like this, there has to be some other reason we're looking at this. Should probably be thinking about my addition and multiplication here to make sure I don't make a mistake. But so there's that polynomial. And now, as much as it looks like it should factor, it doesn't factor. And so we're going to have to use the quadratic formula. And so we know that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Anyways, so working this out, and so actually here we're not working with x. The tune I always start with x, but this is the lambda, right? So we're solving for the eigenvalues. And so we can start to simplify this a little bit, and you might kind of already see what's going to happen here. 16 minus 20 is negative 4 over 2. Well, that's fine. We know what the square root of negative 4 is, right? So this is equal to 4 plus or minus 2 times the square root of negative 1 all over 2. And now I can distribute this 2. And we know that negative 1 is equal to the imaginary number I. And so it turns out that this matrix has two eigenvalues. Lambda 1 is equal to 2 plus I, and lambda 2 is equal to 2 minus I. So this matrix has complex eigenvalues. And so we actually, the definition of what a complex value is fairly straightforward, but we just say that these are complex eigenvalues. And all that is, again, is just an eigenvalue of a matrix, which is a complex number, right? And so we'll quickly, this video actually is mostly just going to be dedicated to reviewing complex numbers. But remember, a complex number is just something that includes a complex term, right? And remember, complex terms are just terms that involve the square root of negative 1. So this I term is what makes these a complex number. And so notice it has two complex eigenvalues, not just one, right? 2 plus I and 2 minus I, which we'll get to later on. And so as we will soon see, although we won't calculate it in this video, these correspond to complex eigenvectors. And complex eigenvectors sound exactly like their definition. They're just eigenvectors that contain complex numbers. And so we would say that the eigenvalues are contained in the set of complex numbers, which we will usually abbreviate with a fancy C like this. And in this case, and actually in the complex case, we're only ever going to be looking at 2x2 matrices. So we know that eigenvectors are contained in the set of all complex numbers or all vectors of length 2 containing potentially complex numbers. So a few quick notes about the set of complex numbers. This is what we call a superset of the real numbers, meaning this set contains, so we'll say contains R and R2 respectively. So notice here that like the set of real numbers is contained in the set of complex numbers. So for example, 3 is technically a complex number, and it'll make more sense when we formally define what a complex number is. But basically what the set of complex numbers allows us to do is add this I term here. And so just keep in mind that like the set of real numbers is a subset of this set. So when we point out, the sets C and C squared, we are also talking about the real numbers along with the complex numbers, not just, the numbers that are strictly complex. So like I said, I actually want to dedicate the rest of this video to just a quick review of complex numbers, some important terms, ideas, and kind of like just things that we'll need to be looking at as we move forward. So throughout, I'll probably use a couple complex numbers just as an example. We'll call them Z1 and Z2. And maybe I will let Z1 equal 4 plus 2i, and Z2 can be 1 minus I. All right. So we can express every complex number like this in the following way. Is of the form Z is equal to A plus B times I, where A and B are real numbers. So notice here, this is what allows us to consider possibly numbers that are strictly contained in the set of real numbers, right? If B is equal to 0, then here we've just got a real number A, right? And so A or B could be any value you want, or any value in the set of real numbers that you want, and every complex number is of this form. So what this actually means, so this number we say has a real part, which is equal to A, is the real part of Z. And Im of Z, which is equal to B, is the imaginary part. And notice when we look at it this way, we don't include the I attached to the Z here, because if we're specifying that this coefficient is attached to the imaginary part of Z, we don't really need to include the I. But what this allows us to do is actually look at, so it turns out that every complex number is a, well, not is, I guess we should say can be thought of as a point in the two-dimensional plane. So what do I mean by that? Well, we have two axes, which maybe at one point we would have called x and y, but now we can just call this the real and the imaginary axis. And so the real axis is the x-axis, the imaginary axis is the y-axis, and now for each complex number, we can think of it as a point that we've plotted in this plane based on its real and imaginary parts. So for example, z1 would be plotted right here, and z2 would be plotted right here. And so it is sometimes very useful, as we'll see looking at some other things concerning imaginary numbers, to think of them as actual points in the two-dimensional plane. And so I think you should then be able to show, right, that basically since each imaginary number sort of corresponds to these two parts, which in a sense are kind of separated by one being imaginary and one not being imaginary, that you could eventually show that the set of complex numbers as a vector space is isomorphic to R2. But we won't really be thinking of it that way today. But if you want sort of a fun exercise, that would be a good vector space exercise to show that as a vector space, the set of complex numbers is isomorphic to R2. All right, so yeah, let's see. So there's a couple then, so leaving that up there, there's a couple operations that are important that we will talk about. So we'll say the modulus of a complex number, z, we usually denote it as absolute value sign z equal to, I have to keep track of everything here, the square root of a squared plus b squared. So this is the basically value of the real part squared plus the imaginary part squared. And again, why does it help to think of this in the two-dimensional plane? Because it turns out that you could also think of the modulus as being the length of this line from the origin to z1, right? So the length of this line would be the modulus of z1 here. And this just follows by the Pythagorean theorem. Right, because notice, so the modulus of z1 is equal to the square root of 20 because z1 is equal to 4 plus 2i. And notice this line is of length 4, this line is of length 2. And if you look at the dotted line I drew along with the lines defined by the axis, they form a right triangle. And so the length of that hypotenuse has to be square root of a squared plus b squared. So we'll come back to this value, the modulus, I think in video 3 of this section when we start looking at matrices again. But this is the modulus of a complex number. Now maybe the one that will be more important immediately, the conjugate. Of a complex number. Z is, we'll denote it usually with this overline notation, so z bar is usually what I'll say. I'll either say the conjugate of z or z bar, and this is just the complex number a minus bi. So all you do to calculate the conjugate of a complex number is multiply the imaginary part by -1 and leave the real part alone. And just because we're relating this back to R2, this would be the equivalent of rotating, or I guess reflecting is a more accurate word, this point around the y-axis, right? So if you imagine reflecting this point around the y-axis in R2, that gives you the conjugate. All right, so we are, and so you can see here that the conjugate of z1 would be equal to 4 minus 2i. So I have a few more things I want to look at, and in terms of these complex numbers. All I want to do is finish up by basically defining addition, multiplication, and division. And so addition and multiplication, I feel, are very straightforward. We'll still look at a couple examples of that. Division is the weird one because, you might have the very prudent question of, how do we divide by a complex number? And basically the answer is we don't. So we'll get there. So addition, you basically just add like terms, right? So let's see. I'll let x equal a1 plus b1 times I, and y equal a2 plus b2 times I. And then I'll do it with the actual complex numbers. So addition of complex numbers, we just add the real parts and imaginary parts. So basically the easier way of describing addition is just group like terms. So if we added z1 and z2, this would be equal to 5 plus I. Multiplication is basically the same thing. There's sort of a small trick you can use to make this go a little quicker if you don't want to have to FOIL each time, but basically multiplication you're just going to be foiling. So if foiling is a little easier to remember each time, then you can certainly just FOIL and everything will always work. But foiling this, you get a1 times a2 plus a1 b2 times I plus a2 b1 times I plus b1 b2. But then here we're going to get times I squared, but I squared is just -1. And so notice grouping like terms, this is equal to a1, a2 minus b1, b2. And this is the real part of this product, plus a1, b2 plus a2, b1, I. And this is the imaginary part of this product. So you could FOIL each time, or you could use this formula. Since I FOILed using the formula, I'll use the formula to do the example. So z1 times z2 is equal to a1 times a2 minus b1 times b2. So this would be minus -2 plus a1 times b2 plus a2 times b1 times I. And so the product of z1 and z2 here would be 6 minus 2I. And you could have also FOILed that in the same way to get this. All right, so all we have left is to define division, and then we will be ready to move back into matrices. So, like I mentioned with division of complex numbers, we don't like to we don't like to divide complex numbers, right? So first, I want to look at what happens if we take some arbitrary complex number, we'll say x, b1i, and its conjugate, which is a1 minus b1i, and multiply x by its conjugate. Well, remember, by definition, this is equal to a1 squared minus b1, or plus b1 squared, right, because it's normally a1 minus b1 squared, but there's two negatives, so we get that, plus a1 times negative b1 plus a1 times b1i. But notice these two terms are equal to 0. So it turns out that the product of x and its conjugate is a real number, which is just a1 squared plus b1 squared, which maybe if you prefer, is equal to the modulus of x squared. So keeping this in mind, that the product of a complex number x and its conjugate is always a real number, now we can define division. Because the way we're going to define division of two complex numbers x and y is x divided by y, we're actually going to define as x times y conjugate divided by y times y conjugate. And basically what you do here, and so of course we're assuming here that y is not equal to 0. But so what we're basically doing here is turning this denominator into a real number. And then we're going term by term and dividing each term of this top product now, which is x times conjugate y, by whatever we get here, by this real number. So we're never dividing by a complex number. We're just dividing by a real number. But notice, since all I'm doing here is multiplying by y conjugate over y conjugate, I'm only multiplying by 1. So I'm actually not changing the value of this number, whatever that means in terms of complex numbers. And so ending with this example, z1 divided by z2 is equal to z1 times z2 conjugate over z2 times z2 conjugate. And so this is equal to 4 plus 2i times 1 plus I over, well, 1 squared plus negative 1 squared. And so this is z2 times z2 conjugate, right, is a1 squared plus b1 squared. So now this product, and I'll FOIL this time. So 4 plus 4i plus 2i minus 2, right? And so that's 2i times I is 2 times I squared, which is just 2 times negative 1, all over 2. And so if you simplify, this is equal to 1. 4 minus 2 is 2, plus 3i. And so that's sort of a slightly easier way to calculate this.